Today, we are strapping ourselves in for a deep dive. We're looking at the absolute foundation, really, of the modern tech economy.
Yeah, we're going past the flashy AI models for a bit.
Exactly, focusing on the underlying stuff, the infrastructure that, makes everything actually work.
The plumbing, so to speak.
Right. So this deep dive, it's about the chips, the AI chips. It's about the huge global investment pouring into data centers and the really massive geopolitical forces shaping where this stuff gets built.
It's a huge map being redrawn.
It really is. We're basically tracking what you could call a $500 billion race to build this new global infrastructure map.
And it's crucial, I think, to get the scale right from the start. Because the numbers we're talking about here, they just dwarf previous tech booms. This isn't just another cycle.
Yeah.
It's like the dominant global investment driver right now.
Yeah.
If you look at the big hyperscalers, Amazon, Google, Microsoft, they've bumped up their capital spending forecast for 2026 hugely by over $80 billion just collectively.
Yeah.
And that alone pushes the whole industry spending forecast over $430 billion.
Wow.
And almost all of that, it's earmarked for building out AI compute infrastructure.
And when you talk about the sheer size of this demand, the numbers start to sound, well, almost unreal.
It is real. Yeah.
I mean, look at Oracle. Just one player, Oracle, announced contracts recently aiming to deliver over $500 billion, $500 billion in computing power.
Over the next 5 years.
Over just 5 years. That single figure, I think, shows the near insatiable hunger for compute power that defines this whole conversation.
It really does. It's completely a seller's market right now. Compute is the hot commodity.
So that massive demand signal, their $500 billion figure, it forces us to start with the engine room, right? The hardware.
The foundational engine, exactly. If AI is the model, these accelerator chips, they're the engines actually doing the math. And right now, we're seeing this incredibly intense, fascinating three-way battle in advanced chips.
Mostly Nvidia, AMD, and Google.
Primarily those three, yeah. It's quite a showdown.
Okay, let's unpack Nvidia first. I mean, they're still the undisputed leader here.
Oh, definitely. Their data center revenues are just astronomical. They hit $22.6 billion in Q1 of their fiscal 25.
Just one quarter?
One quarter. And market share. They're still capturing somewhere between 80 to 85% of the entire AI chip market.
Dominant. And their new architecture, Blackwell, the B200, GB200, that sounds like a big step.
It is. You could even say it's more than just evolutionary. It's an architectural shift. They've moved to what's called a multi-chip module design, or chiplets.
Okay, chiplets. What does that let them do?
It lets them basically stitch together more components, integrate more processing power, and really optimize the performance. The Blackwell B200, it posts some staggering numbers, just starting with memory.
Yeah.
180 gigabytes of this really fast HBM3 memory POO GPU. And that delivers up to 8 terabytes per second of bandwidth. Just massive throughput.
8 terabytes a second. And the performance claims are huge, too. They're saying 3x training performance over the last gen, the H100.
Which is already a beast.
Right. But here's what really jumped out at me, and I think for you listening, too. They're claiming a massive 15x inference performance gain.
15 times.
Yeah.
Specifically in those end-to-end large language model workflows. That's the key.
Why such a big jump in inference specifically?
Well, the secret sauce there is the data format they're optimizing for. The B200 can hit 18 PFLOPS, that's PetaFLOPS.
PETA.
Yeah, PETA, of FP4 tensor operations at its peak. Now, FP4 stands for floating point 4.
Okay. Low precision.
Extremely low precision. See, training these big models often needs higher precision, like FP16 or sometimes even FP32. But once the model's trained, just running it, doing the inference, that can often tolerate much lower precision math.
Yeah.
So by really optimizing for FP4, NVIDIA is maximizing the speed and the efficiency specifically for deploying and using the models.
Yeah.
And that's what the market volume is really shifting towards now.
Right. Getting those models out there and running them efficiently. That's the goal.
Absolutely.
Now, scale that B200 up. You get the GB200 NVL72 node. That's the really big one, right? The full rack system.
That's the ultra performance offering, yeah. It's a full rack designed to house up to 72 of what they call super chips.
Super chips.
Yeah, basically combining the CPUs and GPUs into a single integrated unit. And that whole rack, potentially, can reach an unbelievable 1.44 exaflop-ps of FP4 performance.
Exaflop-ps, that's computational scale we've just never seen before. Brute force.
It's completely unparalleled, and it's exactly what every hyperscaler wants, what they need to train the next generation of absolutely massive AI models.
There's always a but, isn't there?
There is. We have to inject a dose of reality here,
Right.
based on what our sources are telling us. While the chips themselves are technically amazing, the sheer complexity of integrating that full rack system.
You mean power, cooling, all the
Yeah.
connections?
Exactly. Getting the power delivered, the liquid cooling working perfectly, all the high-speed interconnects. It's causing significant supply chain bottlenecks. It's not just about making the chip, it's making the whole system work reliably at scale.
So what does that actually mean for the big customers ordering these, multi-million-dollar racks? When do they actually get them in volume?
Well, the data we're seeing, for example, from TrendForce, suggests that the peak shipment period for that full rack GB200 system, it's going to be delayed.
Delayed, okay.
Yeah. Instead of maybe a massive wave hitting later this year, we're probably looking at that peak delivery window shifting out. Sometime between the second and third quarters of 2025 is the prediction.
So even a relatively minor delay, but in this market.
Exactly. It provides a window of opportunity, a crucial window for competitors.
And speaking of competitors, AMD. They seem absolutely ready to capitalize on any opening. They're closing the gap fast, aren't they?
They really are. Their Instinct MI300 series, that's already gaining serious traction. You're seeing major adoption from huge hyperscalers like Meta, like Microsoft. Those are big design wins.
And their next punch is the MI350 series.
The MI350 and especially the MI355X. These are AMD's direct answer to Blackwell. And they're competing really hard on two main things: price and memory capacity.
Okay, what are they claiming?
Well, AMD is actively out there saying these new chips are matching, or maybe even outperforming NVIDIA's B200 GB200. But the kicker is, they claim they're doing it at a significantly lower cost.
Lower cost per unit of performance.
Yeah, their internal estimates are suggesting the MI355X could offer up to 40% more LLM tokens per dollar you spend on the hardware.
40% more tokens per dollar. That's a very specific, very appealing claim for hyperscalers managing huge budgets.
It's a direct shot at NVIDIA's pricing power. And their other big differentiator right now seems to be memory.
Right. You mentioned memory capacity. Tell us about that advantage.
Okay, so the MI355X, it boasts this enormous 288 gigabytes of HBM3E memory on a single chip package.
288 gigabytes. How does that compare to the B200?
Significantly more. Remember, the Blackwell B200 offers 180 gigabytes, so AMD has over 100 gigabytes more memory right there on the chip.
And why does that matter so much for users?
It matters hugely if you're running truly massive models. Think about models with weights that take up, say, 250 gigabytes. With the MI355X, you can potentially fit that entire model onto a single device.
Without having to split it up.
Exactly. Without needing to shard the model or split it across multiple GPU devices, which adds a ton of programming complexity.
So it simplifies the whole deployment process for these really big models, especially ones needing large context windows. That's a key selling point.
It absolutely is. It reduces the engineering headaches of figuring out how to slice up your model and coordinate computation across many accelerators. It's a big deal for developers.
Okay, hardware sounds competitive, but what about the software? That's always been NVIDIA's ace in the hole, right? CUD.
Precisely. We have to talk about the software ecosystem difference because it's critical. NVIDIA's dominance isn't just hardware. It's cemented by its mature proprietary CDA ecosystem.
It's the standard.
It is the standard. Pretty much everyone in AI has built tools and models on CDA for years. It's deeply entrenched. AMD, on the other hand, is deliberately taking a different path. They're pushing for open source flexibility with their alternative, called ROCm.
Open source. That sounds good on paper. Avoids vendor lock-in, fosters collaboration. So why isn't everyone just switching to ROCm if the hardware is competitive?
Because migrating is a massive challenge. CEA has literally decades of developer time, optimization, and libraries built around it. ROCm is improving fast, actually, but
It's not CEA yet.
it's not CADA yet. Moving a complex, production-ready AI code base from CDA over to ROCm, that requires significant developer effort, time, resources, testing. It's expensive.
So for the big hyperscalers, maybe that investment makes sense for long-term cost savings and flexibility.
That's the calculation they're making, yes. The potential long-term benefits of an open ecosystem and lower hardware costs might justify the migration pain, but for smaller companies or researchers with existing CUDA code bases,
It's a barrier.
it's a huge barrier. That migration difficulty, honestly, remains the biggest protective moat NVIDIA has around its market share, even with AMD making these impressive hardware efficiency gains.
Got it. Okay, before we move off chips entirely, we shouldn't forget the third major player here, Google. They have their own approach, right? Custom silicon.
Absolutely. Google plays a different game. They have their own vertically integrated strategy with their custom tensor processing units, or TPUs. The latest is the TPU V6E, codenamed Trillium.
And their strategy is different because they're not really selling chips directly.
Exactly. It's entirely cloud-centric. The TPU V6E is designed from the ground up to perform optimally within the very tightly controlled, highly efficient environment of the Google Cloud Platform.
So performance is tuned for their ecosystem.
Right. They're reporting a 4.7x jump in peak compute performance and also doubling the memory and the interconnect bandwidth compared to their previous generations.
Interesting. So looking at the specs, the individual chip memory on the V6E looks smaller, maybe 32 GB per chip, compared to Nvidia or AMD, but they scale it differently.
They scale it massively and efficiently. They're optimizing for the total system utilization within their data centers. Google deploys these TPUs in huge configurations they call pods. You can scale up to 256 chips per pod.
256 chips working together.
Yeah, and that gives you a total of 8 terabytes of high bandwidth memory across that single pod system. So their competitive edge isn't selling you the fastest individual chip. It's maximizing the efficiency and minimizing the cost per workload for their cloud customers.
They're selling the integrated service, the outcome, not just the hardware component.
Precisely. It's a different business model focused on their cloud.
Okay, that makes sense. So we've got the chip battleground mapped out. Now let's move from the ships themselves to the actual buildings, the real estate that has to house all this power-hungry gear.
Right. The demand for these accelerators, it requires just a massive build-out of infrastructure, physical data centers.
And this brings us straight into what you called the infrastructure scramble. It's this world where sovereign wealth funds and giant tech corporations are teaming up, co-investing in these physical facilities.
And in doing so, they're essentially becoming the new architects of, well, digital sovereignty. It's a fascinating dynamic.
Let's talk about the scale of investment here. That Aligned Data Centers deal sounded huge.
It is stunning. The headline deal recently was this potential $40 billion acquisition of Aligned Data Centers. They're one of North America's largest private data center operators.
$40 billion, potentially more.
Yeah, the report suggests it could even expand up to $100 billion once you factor in debt financing.
Yeah.
But look at the players involved in this deal. You've got Nvidia, Microsoft, BlackRock, Elon Musk's XAI, and critically, several major sovereign wealth funds. We're talking the Kuwait Investment Authority, Singapore's Temasek, and Abu Dhabi's MGX.
That list. It sounds less like a typical tech acquisition and more like, I don't know, a geopolitical energy consortium or something.
It has that feel, doesn't it? And this acquisition, it's the first major public move by this group called the AI Infrastructure Partnership, or AIP.
AIP. Okay, what's this partnership actually designed to do? What's the strategy?
Fundamentally, the AIP is a financial strategy. It's designed to solve the massive capital expenditure, the CapEx problem, for the tech giants.
How so?
Well, think about it. Traditionally, a company like Nvidia or Microsoft, if they needed massive new data center capacity, they'd have to spend billions of their own capital to either build those facilities or acquire an operator like Aligned.
Right, which ties up a huge amount of their own cash, their balance sheet.
Exactly. It diverts capital that could otherwise go into R&D for chips or AI models. The AIP structure, spearheaded by strategic finance partners like BlackRock, uses a different model.
Okay.
It leverages equity contributions from those deep-pocketed sovereign wealth funds, the ones who want long-term, stable infrastructure returns. This allows the tech companies, like Nvidia or Microsoft, to effectively lease the capacity they need rather than owning the physical real estate outright.
Ah, so it's an asset-light model for the tech companies?
Precisely. It ensures capital-efficient growth for them. It frees up their enormous R&D budgets to focus purely on their core tech chips, software, models, while the asset-heavy infrastructure piece is managed by the financial partners and the SWFs.
And this kind of massive investment is absolutely crucial because, as we said, the global data center market is just struggling to keep pace with this AI-driven demand, especially in Asia-Pacific, right? The shortfall sounds critical.
The numbers really do confirm a looming crisis there. If you look at the operational IT load in Asia-Pacific, it was around 12.2 gigawatts in late 2024. And there's about 14.4 gigawatts in the pipeline, projects planned or under construction.
That sounds like a decent pipeline, 14.4 GW.
It sounds healthy, but the demand projections are just off the charts. The region could be facing a severe shortfall, somewhere between 15 and 25 gigawatts by 2028.
15 to 25 gigawatts short? That's a huge gap.
It's enormous, and you simply cannot run these advanced AI models without a building to put the servers in, and crucially, the power to run them 24/7. It's a fundamental bottleneck.
Which brings us back to the sovereign wealth funds, the SWFs. They're providing the financial muscle for things like the AIP. Why this big pivot? Why are these funds, traditionally known for more conservative investments, suddenly diving so aggressively into digital infrastructure?
It's a strategic shift in perspective. They increasingly view data centers and the underlying digital infrastructure not just as another high-return real estate or infrastructure play. They see it as essential strategic national infrastructure.
Like ports or power grids.
Exactly, on par with owning ports, power grids, major highways, or the main fiber optic trunk lines. As national economies become increasingly digitized, the ability to securely store, process, and control data within your own sovereign borders or through trusted partners becomes paramount.
It's about national security and economic resilience in the digital age.
That's the core driver. It's the new definition of digital sovereignty. Owning or having guaranteed access to compute capacity is becoming a strategic imperative.
And we're seeing concrete examples of this pivot all over the place, not just in that aligned deal.
Oh, absolutely. Look at the Abu Dhabi Investment Authority, ADIA. They recently partnered with SC Capital Partners to launch a specific US $2 billion data center platform just focused on the Asia-Pacific region, Japan, South Korea, Singapore, Australia.
$2 billion just for APAC.
Just for starters. And Abu Dhabi's MGX fund, they're not only in the aligned deal, they're also reportedly a key partner in that absolutely monumental US $500 billion stage initiative focused on AI infrastructure. And Singapore's Temasek is another key financial backer in many of these deals.
So these entities are deliberately positioning themselves as foundational partners in building out the global digital economy's backbone.
Explicitly.
Yeah.
They want a seat at the table, and they have the capital to secure it.
Now, shifting focus slightly, let's look at China. They've also made a really interesting kind of massive structural shift recently to attract more foreign infrastructure investment, specifically targeting these hyperscalers.
Yes, this was a huge regulatory change, quite significant. China launched a pilot program, initially in certain zones, that allows foreign investors to hold 100% equity ownership in some specific telecom services.
What, 100% ownership? That's new, right?
That's the key change. Historically, foreign companies wanting to offer cloud or data center services in China had to navigate these really complex, often restrictive joint venture agreements or other contractual workarounds with local partners.
Which added a lot of risk and uncertainty.
Massive regulatory uncertainty, cost, and operational hurdles. This new pilot program specifically targets what are known as the B11 licenses.
Okay, B11 licenses. Why are they important? What do they cover?
The B11 license category primarily covers things like data center services and content delivery networks, CDNs. Basically, the exact physical and network infrastructure that hyperscalers like AWS, Microsoft Azure, or Google Cloud need to build out their cloud platforms within China.
So allowing 100% foreign ownership makes it much easier, much less risky for them to invest and build.
Exactly. It significantly reduces the regulatory risk profile and the administrative costs associated with those old JV structures. And interestingly, China's Minister of Industry and Information Technology publicly framed this move. He called it a new phase of China's opening up.
A deliberate signal.
A very deliberate signal. It shows a recognition that attracting foreign expertise, technology, and crucially, capital, is absolutely vital if China wants to meet its own enormous internal demand for AI, compute capacity, and advanced cloud services. They need the hyperscalers to help build it out.
So this regulatory shift, it feels like a direct consequence of that global race for capacity we've been talking about. Everyone needs more compute fast.
It's all interconnected. The demand is forcing changes everywhere.
Okay, so we've covered capital flows, sovereign interests, regulatory shifts. Let's pivot back for a moment to the hardware supply chain, and specifically the geographic heart of advanced chip manufacturing, Taiwan. And this idea of the silicon shield.
Right. The silicon shield concept is fundamental to understanding the geopolitics here. Taiwanese foundries, principally TSMC, they account for something like 67% of the entire global semiconductor foundry market.
2/3 of the world's chips.
And if you look just at the most advanced nodes, the ones needed for cutting-edge AI chips and military hardware, their share is even higher. TSMC alone controls about 53% of the total market.
So that extreme concentration of critical manufacturing capability, that's the shield.
That's the core idea of the silicon shield. The world's deep reliance on these chips manufactured in Taiwan acts as a kind of deterrent against military conflict in the Taiwan Strait. Because any disruption there wouldn't just impact Taiwan, it would effectively crash the global economy. Everything from iPhones to F-35s relies on those chips.
But the shield itself seems to be, well, changing shape now. TSMC is expanding globally at an absolutely unprecedented rate. They've got something like 15 plus new fabs either built, under construction, or planned across the US, Japan, Germany.
It's a massive diversification effort.
Which raises this fundamental strategic question. Does this huge overseas expansion dilute Taiwan's leverage? Does it weaken the Silicon Shield?
That is the central debate happening right now among strategists and analysts. It's a really tricky question, with arguments on both sides.
What's the argument for dilution?
The argument for dilution is fairly straightforward. If the most critical advanced manufacturing is no longer exclusively concentrated on the island of Taiwan, then the strategic calculus for any potential aggressor might change. The hostage value of the island's silicon, so to speak, is arguably diminished if alternative sources exist elsewhere.
Okay, that makes sense. But what's the counter argument? The idea that it actually spreads the shield.
The argument for spreading the shield is equally, if not more, compelling to many. By expanding overseas, especially into powerful economies like the US, Japan, and Germany, often incentivized by legislation like the US HEPS Act, TSMC, is essentially creating a network of powerful new allies.
Allies with skin in the game.
Exactly. Proponents argue this globalization means these countries now have a direct, tangible financial and strategic stake in Taiwan's continued stability and security. Because if something happens to Taiwan, their own newly established domestic supply chains, reliant on TSMC's tech and expertise, would immediately dry up or be severely impacted.
So it doesn't eliminate the risk, maybe, but it spreads the economic pain of disruption, directly linking Taiwan's security to the industrial security of its major partners.
That's the theory. It potentially internationalizes the consequences of conflict in a much more direct way.
And meanwhile, the U.S. is certainly not standing still. The CIPS and Science Act back in 2022 allocated over $52 billion specifically to boost domestic semiconductor manufacturing.
Right, that's a huge federal investment. It's an explicit effort by the U.S. to, 1, secure its own technological future, and 2, reduce its critical dependence on those long trans-Pacific supply lines, both for economic and national security reasons.
So it looks like a multi-pronged global strategy unfolding. Taiwan spreads the risk by globalizing, while the U.S. and other allies try to build up their own domestic resilience.
That's right. The stability of the entire AI revolution over the next decade really hinges on the successful and peaceful execution of these massive parallel shifts in the semiconductor supply chain. It's incredibly high stakes.
Okay, let's move down the chain now to regional execution. We've established the global demand, the capital flows, the chip dynamics. But what actually happens when all this investment and ambition hits the ground in specific locations? Australia seems like a perfect case study here. Huge potential meeting, some very real, very physical bottlenecks.
Australia is a fascinating example. On paper, it looks like a top destination. The data center market there is projected to grow at something like an 18% compound annual growth rate through 2030. That's huge growth, making it one of the hottest markets globally, just behind the U.S.
And the big players see that potential.
Oh, yeah. AWS, for example, is pouring $20 billion into Australia between 2025 and 2029. Massive commitment. But the country has this major Achilles heel. And it's painfully simple.
Let me guess. Power.
Power availability. It's the single biggest constraint holding back even faster growth.
How bad is the power bottleneck, really?
It's severe enough that it's completely reshaping where and how these massive data centers get built. According to senior analysts and operators working on the ground there, in the main Tier 1 metros like Sydney or Melbourne, it can literally take years just to get the necessary power infrastructure approved and ready for a new large-scale site.
Years? Why so long?
The existing grid infrastructure in those dense urban areas, combined with the regulatory planning cycles for major power upgrades, simply hasn't kept pace with the sudden, enormous, high-density power demands coming from these new AI facilities. They need huge blocks of power, reliably and quickly. The system wasn't built for that kind of rapid scaling.
Okay, so if the prime metro locations are power-constrained and tangled in red tape, where do the data center operators go? What's the workaround?
They're basically forced to shift their development strategies. They have to look seriously at Tier 2 locations, secondary markets. We're seeing significant moves towards places like Tasmania, for example.
Tasmania? Why there?
Places like Tasmania often offer easier Tier 2 regions have significant potential for renewable energy generation, which is increasingly important for ESG reasons and sometimes for cost.
So moving to secondary markets solves the power and planning bottleneck. But does it introduce new problems?
It definitely can. The big one is often community acceptance, or what the industry calls social license.
The NMBY problem, not in my backyard.
Exactly. Building a massive, potentially noisy, power-hungry data center, even in a Tier 2 location, can face local resistance if it's not handled carefully. Operators are learning they need to engage with the local community extremely early in the process.
What do they need to do to get that social license?
They have to clearly demonstrate the local benefits. That means highlighting job creation, both during construction and operation. It means talking about potential partnerships for reskilling the local workforce for tech jobs. And sometimes it involves showcasing how they might be repurposing old, maybe derelict industrial infrastructure like a century-old factory site for this new, globally relevant AI industry.
So showing tangible local value beyond just building a big box.
Precisely. Without that community buy-in, even a project with available power and land can get bogged down in local opposition and delays. It's a crucial hurdle.
This constant friction we're seeing between the ideal location for latency versus where you can actually get power and permits, it's driving a bigger, more philosophical debate, isn't it? About where AI compute should actually live, the whole centralized mega factory versus the distributed edge model.
That's a huge debate right now, yeah. And the answer seems to be, it depends on the workload.
Okay, explain that. When does the centralized model make sense?
For the really massive compute-intensive workloads, think training those enormous foundational AI models that take weeks or months, or doing large-scale batch processing for things like scientific simulations, drug discovery. In those cases, the centralized model is often optimal.
These are the AI factories.
Exactly. We're talking multi-hundred megawatt campuses, sometimes located in quite remote areas, specifically chosen because power is extremely cheap and abundant, maybe near large hydro dams or renewable energy zones. For these workloads, latency usually isn't the absolute top priority. Cost, scale, and power efficiency are the main drivers.
But then, the moment AI starts moving into applications that interact with us in real time, consumer apps, enterprise tools, autonomous systems, latency becomes critical.
Latency becomes everything. If you're dealing with real-time video processing or generating speech instantly or making decisions for an autonomous vehicle, you need that computation to happen incredibly close to the end user or the device. Milliseconds matter.
And that's where the edge comes in.
That's what drives the demand for compute capacity, located right in, or very near, the major metropolitan areas. This is the edge compute layer. It's about proximity.
Is it just edge data centers, or are we seeing other models emerge?
It's often a hybrid. We're seeing demand for smaller, low-latency edge data centers in metros. But interestingly, we're also seeing signs of a potential return to on-prem model for some enterprises.
On-premise, back in their own buildings.
Yeah, some large enterprises with very specific latency-sensitive AI workloads might choose to host some compute capacity directly on their own premises again, to guarantee absolute minimal latency and perhaps data control for their critical operations. But typically, this would still be coordinated with larger cloud resources.
This whole centralized versus edge thing, it sounds a bit familiar, like a pattern we've seen before in tech.
It absolutely mirrors, in some ways, the evolution we saw with mobile devices and cloud services. Remember when smartphones first came out? Initially, services were often built assuming weak devices and networks, so a lot happened centrally.
Right.
But then the devices themselves became incredibly powerful. Networks got faster, and the industry kind of commoditized the middle ground. The current expert consensus seems to be leaning towards a similar hybrid model for AI.
So how does that hybrid model work?
The idea is that many edge AI services will likely coordinate actions between the increasingly powerful end device, your phone, your car, your factory robot, and the massive centralized data centers where the really heavy lifting and model updates happen. But that localized compute capacity, the edge node, is essential for enabling that truly seamless real-time interaction. You need both.
That need for localized, low-latency capacity connects directly to the networks that link everything together, which brings us neatly to this idea of network as a service, or NaaS, and how companies are thinking about owning the underlying infrastructure. We saw Telstra International, for instance, making a very deliberate strategic shift towards treating connectivity as a network, as a product.
Yes. Their strategy is really interesting. It focuses intensely on owning and controlling the actual fixed infrastructure. We're talking about the subsea fiber optic cables connecting continents, the landing stations where those cables come ashore, and the terrestrial fiber backhaul networks that distribute capacity inland.
Why is owning the physical assets so critical for them to deliver this NaaS model?
Because for carriers like Telstra, owning the physical fiber and then lighting it yourself, meaning deploying your own advanced optical transmission equipment on that fiber, provides by far the best unit economics, the best cost per megabyte transported.
Better than just leasing capacity from someone else.
Much better. It allows them to bypass what can be expensive, often restrictive, wholesale capacity leases from other infrastructure owners by controlling the entire platform end-to-end, from the subsea cable right to the data center door.
They control the performance and cost.
Exactly. They can offer highly flexible, scalable, and importantly, guaranteed bandwidth on demand. They can tailor connectivity solutions very precisely to the enormous, often fluctuating demands of modern AI data centers and cloud providers. It transforms connectivity from just being a dumb pipe or a utility into a customizable, high-value service.
And the underlying economics of owning these big infrastructure assets like subsea cables are actually being dramatically rewritten by the very hyperscalers who are driving the AI boom.
Yes, that's a crucial dynamic. Over the next few years, analysts project something like US $13 billion will be invested globally in new subsea cable infrastructure.
$13 billion.
And here's the truly astonishing fact. Hyperscalers like Google, Meta, Microsoft, Amazon, they're expected to account for over 75% of that massive investment figure.
75%. So they're literally becoming the biggest funders and owners of global internet connectivity infrastructure themselves.
In many ways, yes. They need so much inter-data center bandwidth globally that it makes economic sense for them to directly invest in or co-build these massive cable systems.
So how does their huge investment help companies like Telstra running NOS platforms?
It fundamentally improves the cost base and the availability of raw fiber capacity for everyone, including the carriers building these integrated NOS platforms. It creates this powerful, self-reinforcing loop, a kind of infrastructure flywheel.
Explain that flywheel.
Okay, the massive demand for AI compute from hyperscalers drives them to invest heavily in global connectivity, subsea cables. That huge investment lowers the overall cost and increases the supply of fiber globally, which in turn makes it more economical and feasible for carriers like Telstra to build out their own infrastructure NOS platforms, which then allows them to better serve the hyperscalers and others' connectivity needs.
So demand drives supply, which enables better service, which fuels more demand.
Exactly. The key takeaway is that the NOS revolution isn't just a fancy software overlay. It's deeply anchored in the strategic decision to own and control the physical pipes, because that's what provides the necessary flexibility, guaranteed performance, and cost economics required by modern high-stakes AI applications.
Okay, we've spent a lot of time talking about the race for capacity, building bigger chips, bigger data centers, bigger networks, but there's a giant elephant in the room. The sheer energy consumption of all this infrastructure, it seems unsustainable.
It is. The energy issue cannot be overstated. Global data center electricity usage is already enormous, consuming maybe 1–2% of global electricity today. But projections suggest it could nearly triple by 2030, potentially reaching somewhere like 4–6% or even more of total global power capacity, driven almost entirely by AI workloads.
That kind of growth is just not sustainable on current grids.
It's deeply problematic. It demands a radical paradigm shift in efficiency. And this is precisely where neuromorphic computing enters the conversation. It's positioned as potentially AI's radical answer to this looming energy crisis.
Neuromorphic computing. Okay, break that down for us. What does that actually mean? How is it different?
It's fundamentally brain-inspired computing. Traditional computers are based on the von Neumann architecture, where you have separate processor and memory units, and data constantly shuffles back and forth between them. That data movement is incredibly power-hungry.
Okay.
Neuromorphic processors work differently. They try to replicate the brain's structure and function. Computation and memory are often integrated much more closely, sometimes right together in artificial synapses and neurons. And critically, they operate asynchronously and are event-driven.
Event-driven, meaning?
Meaning the chips, or parts of the chip, only consume significant power when they are actively processing an incoming event analogous to a neuron firing a spike in the brain. When there's no input or activity, they consume very little power. It's not constantly clocking and burning energy like a traditional CPU or GPU.
And the efficiency gains from this totally different architecture are significant.
They are potentially phenomenal. We're not talking incremental improvements here. Research systems and early chips are demonstrating potential energy efficiency gains of up to 100,000 times compared to traditional silicon for certain types of tasks.
100,000 times less energy. That's not just a shift. That's a revolution if it scales.
It completely changes the infrastructure planning model if it proves viable for widespread AI tasks. Think about it. IBM's True North chip which was an early large-scale neuromorphic system, used just 26 picojoules. That's trillionths of a joule per synaptic event. Incredibly frugal.
So what are the implications if this technology matures? Where would it be used?
The big hope is for deployment at the edge. Imagine putting these incredibly energy-efficient neuromorphic systems directly into devices, sensors, cameras, robots, maybe even smartphones or wearables. If they can handle a significant portion of the AI inference tasks right there at the device level, using minuscule amounts of power.
It could drastically reduce the load on the big, power-hungry centralized data centers.
Exactly. Some projections suggest that effectively deploying neuromorphic computing at the edge could potentially reduce the workload hitting centralized data centers by as much as 90% for certain types of inference-heavy applications.
90% reduction in data center load. That would completely change the capacity and energy crisis narrative overnight.
It would be transformative. We're already seeing practical applications starting to emerge in areas like advanced prosthetics that learn user intent, ultra-low power diagnostic devices, and automotive research for driver assistance systems, all demonstrating these thousand-fold or more energy reductions in real-world scenarios compared to conventional approaches. It's still early days for widespread commercialization, but the potential is immense.
So while the engineers are dreaming up these incredibly efficient future chips, the people running today's infrastructure, the operators, are still dealing with some very tangible, very physical, high-stakes problems right now.
Absolutely. Day-to-day operations have their own challenges.
Which brings us to another interesting angle, the digitization of existing physical infrastructure, specifically the example of cell towers and the immediate financial impact of just having accurate data about what's physically out there.
Yes, this is a massive, often hidden operational problem, particularly for large companies that own and manage thousands of cell towers globally. These are assets worth millions, scattered across vast territories. But often, the company lacks truly accurate, up-to-the-minute data on exactly what equipment is installed on each tower and where.
How can that be? Don't they track installations?
They do, but traditional methods, manual surveys, relying on potentially outdated records are slow, can be dangerous for climbers, and are often surprisingly inaccurate down to the centimeter level, which matters for things like antenna alignment and available space.
And having inaccurate data leads to real financial losses.
Huge revenue leakage and unnecessary costs. This lack of precise, trustworthy information leads to all sorts of chronic problems. Things like underleasing the available space on a tower because they don't know exactly what will fit where.
Leaving money on the table.
Exactly. Or overcharging clients based on incorrect or outdated estimates of the equipment they have installed. And particularly in high-growth, less regulated markets, say in parts of Africa or Asia, you even see problems with unauthorized equipment being installed on towers by other operators without payment.
Wow. So how does technology solve this fundamental mismatch between the digital record and the physical reality on the tower?
The solution that's gaining traction is this combination of autonomous drone surveying coupled with AI-powered digital twin technology. There are platforms like vHive, for example, that specialize in this.
Okay, how does that work? Drones fly around the tower.
Pretty much. The drones conduct automated, pre-programmed survey flights around the tower, capturing thousands of high-resolution images from all angles. Then, AI software processes all those images using techniques like photogrammetry to build a highly detailed, dimensionally accurate 3D model, a digital twin of the tower and all the equipment on it.
How accurate can these digital twins be?
We're talking millimeter-level accuracy on things like antenna size, its exact position on the tower structure, even its precise tilt and azimuth direction. The AI can automatically identify different types of equipment, measure dimensions, and compare it against the existing database records to flag discrepancies. It can spot an antenna that's tilted just 1 degree off from where it should be, which can significantly impact network signal quality.
And the financial impact for the tower company of implementing this kind of digitization, is it significant?
It's often immediate and substantial. Studies and operator reports show that using drones and AI for inspections can slash the direct costs of tower inspections by up to 70% compared to manual climbing methods.
70% cost reduction.
And perhaps even more importantly, by providing accurate inventory and identifying issues quickly, it can minimize revenue loss from things like billing errors, unauthorized use, or network downtime caused by misaligned antennas by up to 90% in some cases.
90% reduction in revenue loss, just by knowing exactly what you own and where it is.
Exactly. It proves that simply having accurate, timely data about your physical assets translates directly and immediately into better operational efficiency, optimized costs, and assured revenue.
Right.
It's a powerful example of digitization impacting the physical layer.
Okay, we've covered an incredible amount of ground. We've navigated the chip wars, the massive flow of capital from sovereign funds, the geopolitical tensions around supply chains, the physical constraints of power and land, and the technological push towards efficiency with neuromorphic indigenization.
Yeah, it's a complex ecosystem.
It really is. Finally, I think it's worth looking beyond just the hardware, the money, the tech specs, and considering the kind of mindset, the leadership philosophy that's required to actually navigate this brutally competitive, incredibly high-stakes technology environment. We came across a fascinating perspective on this from Eric Boonstra. He's the CDO of Kevlin's Data Centers.
Yeah, Boonstra's perspective was really interesting because he draws these direct and very powerful parallels between running a high-pressure data center business in this volatile market and his own deep background in martial arts, specifically kickboxing and taekwondo.
So for him, it's not just a hobby, it's actually integrated into his leadership approach.
Very much so. He talks about it not just as physical training, but as a foundational philosophy for leadership, especially in demanding situations.
What are some of the key principles from martial arts that he feels translate most effectively into business strategy, especially in this AI infrastructure world we've been discussing?
One of the main things he emphasizes is the need for absolute unwavering focus. He uses the analogy from sparring or fighting. You cannot be 99% focused. You need to be 100% focused. Otherwise, you get kicked or punched.
Total concentration.
Total concentration. And he argues that same level of 100% mental clarity and presence is required when you're making strategic decisions, managing risks, or overseeing the execution of these huge multi-billion-dollar data center build projects, where a single supply chain failure or miscalculation can be absolutely devastating.
That intense focus makes sense. But this market is also changing incredibly fast, so that focus presumably needs to be coupled with adaptability, right?
Absolutely. And that's where his other favorite reference comes in. He often quotes the famous Mike Tyson observation, everybody has a plan until they get punched in the face.
Right.
And this industry, the AI infrastructure sector, is constantly delivering those unexpected punches, whether it's a sudden delay in a critical component like the GB200, a surprising new regulatory shift coming out of China, or hitting an unforeseen massive power constraint in a key market like Sydney.
The plan needs to survive contact with reality.
Exactly. So Boonstra's philosophy, informed by martial arts, is about having the mental discipline and the resilience to immediately react when that punch lands, to absorb the shock, assess the new situation instantly, and adjust the strategy without hesitation or panic. It's about developing that reflexive adaptability.
So it's not about avoiding the punches, because you can't, but about how you react and recover. He also talked about balance, didn't he? But maybe not in the way people usually think about work-life balance.
Right. He kind of reframes it. He suggests that true balance, especially in such a high-intensity field, isn't necessarily found by trying to completely switch off or compartmentalize. Instead, it's about integrating the physical fitness and the mental rigor developed through something like martial arts into the work itself, so that you're building the stamina and the mental toughness required to sustain high performance and readiness continuously.
A philosophy of continuous readiness, then. Always prepared for the next round, the next market shift.
It seems like a very fitting analogy for the incredibly dynamic and demanding environment that we spent this whole deep dive exploring. This entire sector is defined by intense pressure, high stakes, and constant, often unpredictable, shocks to the system.
Well, we have certainly covered a remarkable amount of ground today. We started right down at the foundational level, with the chips themselves. Nvidia's push for colossal capacity with Blackwell, AMD's aggressive counter on memory and cost efficiency with the MI350 series, and Google's very specialized cloud-centric scaling approach with Trillium TPUs.
Then we track the money, that massive flow of global capital, increasingly driven by sovereign wealth funds who are viewing data centers not just as real estate investments, but as a core strategic national infrastructure. We saw how mechanisms like the AIP are being used to finance this build-out efficiently.
And we explored those crucial friction points along the way, everything from the complex geopolitical tensions surrounding Taiwan's shifting silicon shield and the global semiconductor supply chain,
Right down to the very tangible on-the-ground constraints, like Australia's struggle to provide enough power quickly enough in key locations, forcing operators into new strategies and meeting that social license.
We also touched on the critical importance of controlling the network infrastructure through models like NOS, driven by owning assets like subsea cables.
And looked ahead to the radical potential of neuromorphic computing to address the looming energy crisis through brain-inspired efficiency, alongside the immediate benefits of digitizing existing physical assets like cell towers.
It really feels like the future of AI infrastructure is being defined by this intense simultaneous race for two critical things: massive scalable capacity on one hand.
And on the other hand, the urgent, absolutely non-negotiable need for radical efficiency, energy efficiency, cost efficiency, operational efficiency to actually sustain that capacity growth in the long term. And these two demands, capacity and efficiency, are sometimes pulling investors, innovators, and strategists in slightly different directions.
Which brings us to our final thought for you, the listener. Based on everything we've analyzed today, all the sources and trends we've discussed, here's something provocative to leave you with.
We know that the cutting-edge chips coming out now, like Nvidia's GB200, are marvels of engineering designed for unbelievable brute force computation, aiming for performance peaks like 1.44 exaflop PS, just raw power.
Yeah.
But we also know that these radically different brain-inspired neuromorphic systems are demonstrating potential energy efficiency gains that are orders of magnitude better, maybe up to 100,000 times more efficient for certain tasks.
So here's the question. When you consider the long-term sustainability, the escalating energy costs, the environmental impact, and the sheer global scalability required for deploying AI truly everywhere, who do you think will be the ultimate winner in this infrastructure race over the next decade or two?
Will it be the company that achieves the absolute largest scale of centralized brute force compute power, like that 1.44 exaflop PS? Or could it be the company that first truly masters and scales that incredible thousand-fold energy efficiency gain likely deployed out at the distributed edge?
Raw power versus extreme efficiency. You've heard the arguments, you've seen the trends, you have the information now to think about which bet might be the smarter one for the long haul.
It's a fascinating strategic choice, isn't it? How you choose to balance those two fundamental forces, capacity and efficiency, really defines the next chapter in this convergence of deep technology and global finance.
Join us next time as we continue our deep dive into that convergence, exploring where capital meets capability.